Let's finally take a look at the efficiency of the vapor compression cycle. First, let's define what is an efficiency. An efficiency is an economic parameter. The efficiency is often written with the letter theta and eta, sorry, and it's the ratio of two absolute values. These absolute values are absolute energy or power transfer, and it's the ratio between the power we gain divided by the power we pay, or the energy we pay. So that's what I mean by an economic parameter, because it's an economical point of view which will define if a given power exchange corresponds to something we pay, to something we gain, or in some cases to something neutral that will not even be taken into account in the efficiency. Here I just want to highlight one thing, is that quite often the expression of the efficiency can be also written as the ratio between an energy exchange divided by the maximum energy exchange that could be reached. In that case, the efficiency is always between 0 and 1, because we get 1 when we get the highest energy exchange in the machine that could be possible. It's not the case especially for the application of this efficiency to a vapor compression cycle. The power we gain may be higher than the power we need to pay for the machine to be working, because some energy transfer will be considered as neutral. So, in order to explain a bit, to write a bit further what energy transfer corresponds to the upper or lower side of this ratio, we need to think about what is the purpose of the machine. And a vapor compression cycle can be used for two purposes. The purpose is always a heat transfer, but either the goal is to heat up the hot source. In that case we call it a heat pump, or in other cases it's to remove heat from the cold source, and in that case it's called a refrigeration machine. And in both cases, in each of these two cases, the efficiency will be defined differently. So if I take the first use of this machine, a heat pump, the efficiency of the cycle for heating is called a coefficient of performance. So that's the little name that is most of the time given to it. And here the power we gain is the heating power to the hot source. So it is directly the heat transfer between with the hot source, so between B and C. And we only want a positive value for the efficiency, so we take only the absolute value. The power we need to pay is the technical work that is provided by the compressor to the fluid, because in fact what we need to pay usually is the electricity that will supply the electrical motor that will run the compressor. So the power we pay, if we take as system only the cycle of the thermodynamic fluids, corresponds to the technical work between A and B. And as we have seen before, the expression of the can simplify this ratio by expressing it only as a function of the specific enthalpy of this given point, and that would correspond to HB minus HC over HB minus HA. So it's possible to express the efficiency of the cycle only with these three specific enthalpies. Now, if we use the machine as a refrigeration machine, the efficiency of cooling is called the coefficient, in French it will be coefficient d'effet frigorifique. In English I think it's probably cooling efficiency, and it's sometimes written with the letter epsilon. And in that case, the power we gain is the heat transfer with the cold source, because the purpose of the machine is to cool down the cold source. So here we have the heat transfer between D and A, so the heat exchange inside the evaporator. What we need to pay is the same thing than before. It's the technical work that is provided to the compressor, so the technical work received by the fluid between A and B. And once again, we can express this efficiency only as a function of the specific enthalpies of this characteristic point. So that would be HA minus HD over HB minus HA. You can note one thing is that for a given machine, the coefficient of performance is equal to the cooling efficiency plus 1. That is just due to the way it is written, and to the fact also that HD is equal to HC. So that's it for the efficiency.